Hello, and welcome to today's lesson on calculating thermal energy. Today, we will learn what specific heat capacity is and how it relates to the energy required to change the temperature of a substance. We will learn how to use the equation E equals mc delta theta to calculate the energy needed to change the temperature of a substance and practice applying it to various scenarios. So far, you have become familiar with thermal energy and how it relates to the temperature of materials. Building on this foundation, we can now explore the concept of specific heat capacity, which will deepen your understanding of how different materials respond to thermal energy. This will help us build on our qualitative understanding to introduce how we quantify thermal energy. Specific heat capacity is a fundamental concept in thermal energy, helping us understand how different materials respond to changes in temperature. Think of it as a measure of how stubborn a substance is when it comes to changing its temperature. To illustrate this, let's consider a hot summer day. Imagine walking barefoot on a sandy beach and then stepping into a shallow pool of water. You'll notice that the sand feels much hotter than the water, even though both the sand and the water are exposed to the same sun. This difference is due to the specific heat capacity of the materials involved. Water has a higher specific heat capacity than sand, meaning it requires a lot more heat to raise its temperature. Therefore, the water feels cooler to the touch compared to the sand. The high specific heat capacity of water is actually crucial for many reasons. Our bodies are mostly made of water, and this high specific heat capacity means that our body temperature doesn't increase too much when we exercise or cool down too much when we go outside on a snowy day. Water helps regulate our body temperature, maintaining it within a stable range. At its core, specific heat capacity helps us understand how different materials respond to temperature changes. Materials with higher specific heat capacities require more heat energy to change their temperature, while those with lower specific heat capacities heat up or cool down more quickly. More formally, specific heat capacity is defined as the amount of heat energy it takes to raise the temperature of a substance by 1 degree Celsius or 1 Kelvin. Now let's move to an important equation that uses the concept of specific heat capacity, E equals mc delta theta. This equation helps us calculate how much energy E is needed to change the temperature of a substance. It tells us that the energy required depends on 3 factors: the mass, m, of the substance, its specific heat capacity, c, and the change in temperature, delta theta. The mass is simply the amount of the substance you have. For instance, if you have a small pot with a little water, you'll need less energy to bring it to its boiling point compared to a large pot with more water. Hence, the higher the mass, the more energy you need. As we've discussed, specific heat capacity is a property that tells us how stubborn a substance is in changing its temperature. Different substances require different amounts of energy to change temperature. The higher the specific heat capacity, the more energy you need to put in. The change in temperature is the desired difference in temperature you want to achieve. For example, if you want to heat water from room temperature, about 20 degrees Celsius, to boiling, 100 degrees Celsius, you care about the change in temperature, which is 80 degrees Celsius. The bigger the temperature change, the more energy you will need to add. Consider heating water in a pot. If you want to calculate how much energy you need to get the water to a certain temperature, you would use the equation E equals mc delta theta. For instance, if you have 2 kilograms of water, the mass, and want to raise its temperature by 50 degrees C, and knowing the specific heat capacity of water is approximately 4,180 joules per kilogram degrees C, you can calculate the energy required. This leaves us with 2 kilograms times 4,180 joules per kilogram, degrees C times 50 degrees Celsius. Solving this equation leaves us with 418,000 joules. So you would need 418,000 joules of energy to increase the temperature of 2 kilograms of water by 50 degrees Celsius. Let's apply what we've learned to a few specific problems to consolidate our new knowledge. First, calculate the energy required to heat 2 kilograms of water from 20 degrees Celsius to 80 degrees Celsius. The specific heat capacity of water is approximately 4,200 joules per kilogram degrees C. Identify the known quantities. Mass equals 2 kilograms. Specific heat capacity equals 4,200 joules per kilogram degrees C. The initial temperature is 20 degrees C and the final temperature is 80 degrees C. Now calculate the temperature change by carrying out final temperature minus the initial temperature. This leaves us with 60 degrees C. Finally, we can substitute our values into the formula. E equals 2 kilograms times 4,200 joules per kilogram degrees C times 60 degrees leaves us with a final value of E equals 504,000 joules. Therefore, the energy required is 504,000 joules. Let's move on to another problem. Determine the energy needed to raise the temperature of 0.5 kilograms of copper by 50 degrees C. The specific heat capacity of copper is 385 joules per kilogram degrees C. First, identify the known quantities. Mass equals 0.5 kilograms, specific heat capacity equals 385 joules per kilogram degrees C, and temperature change equals 50 degrees C. Now use the formula. E equals 0.5 kilograms times 385 joules per kilogram degrees C times 50 degrees C. This gives us 9,625 joules. Therefore, the energy needed is 9,625 joules. Let's look at one final problem. How much energy is required to heat 3 kilograms of iron from 25 degrees C to 150 degrees Celsius? The specific heat capacity of iron is 450 joules per kilogram degrees C. First, identify the known quantities. Mass equals 3 kilograms. Specific heat capacity equals 450 joules per kilogram degrees C. Initial temperature equals 25 degrees C, and the final temperature equals 150 degrees C. Now calculate the temperature change, delta theta, by carrying out final temperature minus the initial temperature. This leaves us with 125 degrees C. Now use the formula. E equals 3 kilograms times 450 joules per kilogram degrees C times 125 degrees C. E equals 168,750 joules. Therefore, the energy required is 168,750 joules. By working through these examples, you observe the steps for identifying the relevant quantities, calculating the temperature change, and using the formula E equals mcΔθ to find the energy required. This process highlights the practical application of specific heat capacity in energy calculations. In this lesson, we've covered the concept of specific heat capacity and how it relates to thermal energy, defining it as the amount of energy required to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. Next, we introduced and discussed the equation E equals mcΔθ, which helps us calculate the energy needed to raise the temperature of a substance. By understanding the quantities involved, mass, specific heat capacity, and temperature change, we can predict and calculate the energy requirements for different thermal processes. We applied the equation to solve several problems, further consolidating our knowledge. This comprehensive understanding of specific heat capacity and the E equals mcΔθ equation is vital in explaining how energy is transferred in physical systems and helps in real-world applications such as heating systems and thermal management.